All right, everyone, I have 6:10. Let's go ahead and get started. Before I do, anybody have any questions about anything at all? All right. You may not have noticed, I recently put in grades for the first homework assignments. Basically, I'm going to have my homework assignments be out of 100 points, and I just put in the percentage that I got from web work. So by tomorrow, if there was anything on there you had problems with, or you just maybe want to see another way to get those things done, the solutions should open up tomorrow at 5. So if there were anything on there that you had questions about, consult the solutions when they come up tomorrow. I think the solutions are pretty detailed, but if you still have questions, like always, you can set up an appointment with me, come to office hours, reach out to me over email, reach out to somebody on Slack, whatever you need. But yeah, if you need help, there are ways to get it. So we're going to continue on with work. So one thing that I wanted to talk about was this problem we looked at last time. And one thing, and this is totally my responsibility, one thing we needed to do was to basically get everything in the right units. So it's very important to have consistency early on. So one thing we really need to do here is modify these lengths in centimeters to be written in meters. So this will be 0.1 meters, and this will be 0.15 meters. All right, so I'm going to kind of fast forward a little bit because we did a lot of this on Thursday of last week. And you know what? Since this happened last week, and I want to make sure. Can someone confirm that we can hear each other?
Can confirm.
Yeah, we can
Excellent.
hear you.
Okay. And I apologize again for that last week. I'll be more careful. All right, so we want to know how much work it takes to stretch the spring like this. One thing we have to be mindful of is Hooke's law. So, you know, a spring that follows Hooke's law has this proportionality where the force increases as a linear function of how much extension or compression, basically how much displacement from its natural length you put on it. So we know that when we extend this spring by 0.1 meters, or no, by 0.05 meters, that results in a force of 40 newtons. So from there, we can get a stiffness constant of 800 newtons per meter. So hopefully that number looks familiar from last week. I think that's about where we ended up reliably. So if you want to find the work, remember that in general, and I mean, this becomes simpler if you have a constant force, but we have a variable force here. In general, our force is going to look like this. You're integrating some force function over some displacement. And that displacement, basically, you're doing that over some given interval in x. So this second bullet here, how much work is needed to stretch the spring from, basically, I'm displacing it from its natural length. So let's go ahead and start filling in this integral. Its natural length is going to be x equals 0. And one note I'm going to put here is x is going to represent displacement from natural length. So since I'm starting my natural length, my initial displacement is going to be 0. And its natural length is 10 centimeters. I'm extending the spring to a length of 15 centimeters. So that means my final displacement is going to be 0.05. and I'm integrating my force function, which I found from my one data point, which is 800x dx. And since it's been a few days since we've all looked at this together, just want to stop here. Anybody have any questions about how we ended up here? All right, so what is the antiderivative of 800x?
800x squared. 400x squared.
400x squared. And evaluated from 0 to 0.05. I believe that comes out to be 1 joule. And second bullet here, how about if I want to stretch it another 5 centimeters? So now, and just in case I wasn't clear enough about this last bullet here, I'm assuming that it has already been stretched to 15 centimeters. So my initial displacement will be 0.5, and my final displacement will be double that, or 0.1. Same function. Same antiderivative. And that's going to come out to 400 times 0.1 squared minus 400 times 0.05 squared, which this one's going to be 4 joules minus 1 joule, which is equal to 3 joules. So one thing I want to point out before we go too much further is that notice that the force acting on the spring is linear with respect to that displacement, but the work is not going to be. And I'm hoping that's clear why that's the case. But we can definitely talk about it if you're not understanding why that would be the case. For example, if you are expecting that second calculation to give you 2 joules, just double the original. But before I go on, anybody have any questions about this first example here? All right, let's dive into our next one. So let's do one in English or imperial units here. So I know the work required to stretch a spring 1 foot beyond its natural length is 12 foot-pounds. How much work is needed to stretch it 9 inches beyond its natural length? All right, so I'll let you all drive now. How should I start this thing?
I guess so you could start by defining variables. So like force is for 1 foot is 12 foot-pounds.
Okay, so yeah, we know force at 1 foot. And so you're saying force at 1 foot is 12 foot-pounds. What is foot-pound really a measurement of?
Weight.
Now, foot-pound is not a measurement of weight.
It's density.
It's not density.
Work.
This is work. So can't really equate them, and maybe that's not what you said. That's what I thought I heard. But based on what I know is this: I know that when x equals 1 foot, that leads to a work of 12 foot-pounds. We can assume that this spring is, kind of beholden to Hooke's law. So there has to be some stiffness constant. I don't know what that stiffness constant is yet. In the last example, I knew that when I extended it a certain length, there was a known force acting on it. I don't have that here. All I know is that
Just before we press on, I think I'm got a little bit confused 'cause in the imperial units, I thought you said that like force and weight were, or work and weight were the same thing, or maybe that was force and weight.
So let's talk about one of those at a time. So you said force and weight. A weight is a type of force. I mean, force is a more general term for like any kind of a push or a pull, and weight is, one such thing that fits that description. So yeah, weight is measured in pounds. Pounds are a measurement of force in the imperial system. But there is a difference between pounds and foot pounds. So a force does not rely on any kind of displacement or distance. Just like in metric, we refer to force as, we measure force in newtons, but we measure work in Newton meters or joules. Was that what you were after, Alistair?
Yeah, I think I just got my wires crossed
Yeah.
for a moment, but thank you.
Yeah, no problem. Yeah, and then force and work, especially if you haven't dealt with it before, they're similar enough that it's easy to confuse them. All right, so back to this, I need to figure out, what this stiffness constant is. But there is I don't have a point for like when x equals this, the force equals this. So is there another way I can figure out what this unknown constant K is? Is there some relationship between force and work that I can rely on?
Isn't integral force like work?
Yeah, absolutely. So I know this in general. So some definite integral of work is equal to f of x dx. So right now, all I know about my force function is that it's kx. Oh, that's okay. That might be all I need to know. What should my limits of integration be for me to go on?
Zero to one.
0 to 1, yeah. So I want to keep this whole thing in feet. I want to keep all my distances in feet and my forces in pounds. So this is the integral I want. But I also know that the work is equal to 12 foot-pounds. So if I evaluate this integral, I should be able to back solve for that value of K. So getting the antiderivative here, 1/2 kx squared, evaluated from 0 to 1 equals 12. So that's 1/2 K times 1 minus 1/2 K times 0 equals 12. So I get 1/2 K equals 12, which means K is equal to 24. So that's a big piece of this puzzle. So how much work is needed to stretch it 9 inches beyond its natural length? So now that we have K, we should be able to make that calculation. Someone tell me how to write out that calculation to find that work.
Half kx squared. I don't know.
So it would be 12 plus the integral of 1 to 9, 24 x dx.
Oh, so I'm not stretching it 9 inches beyond that first foot. This is purely just an extension of 9 inches.
Oh,
So I'm going from 0 to something.
0 to 9 then.
So be careful. It's not actually going to be 9 because what units do I want to keep all my distances in terms of?
Professor,
Yeah,
can you
Rios.
sort of like directly apply the half kx squared, like since it's from 0, like you just have the top function, or like the 9, right?
Is half the what function?
No, like the half kx squared, because it's like, because it's from 0, so you don't need to actually integrate the
Yeah,
entire thing.
you're absolutely right. So yeah, the work is equal to 1/2 kx squared, which we just figured out is 12 kx squared. So yeah, you're absolutely right. There's no need to do another integral. Really, all we have to do from here is just figure out what value of x makes sense for us. What's that going to be?
Like 3/4.
Yeah, it's going to be 3/4. Yeah, because yes, that unit is given, that length is given to us in inches, but we're dealing in foot-pounds, so we got to be consistent to both of those units. So this comes out to be 12 times 9/16, which is like 27/4. So 6.75 pounds. All right, any questions on this one? All right. All right. So get into a little more in-depth in problem solving now. So we have a situation here. I have a 200-pound cable, a heavy cable that's 40 feet long and hangs from the top of a building. How much work is required to lift the cable all the way up to the top? All of the cable all the way to the top. So let's just draw a basic sketch of what's going on here. Here's my tall building. Here's a winch or something, and this cable's hanging down. "40 feet in length. So we want to pull this all the way up. And, we've looked at a lot of different situations in terms of work, but one thing to keep in mind is that work is equal to, at a basic level, force times displacement, but in general, this integral, f of x dx. So I'm integrating some force function over some distance. So what force am I dealing with here? So as I pull this rope up, what is actually going to be resisting me?
Gravity.
Gravity, right? And specifically the gravity or the weight of what?
The gravity acting on the weight of the cable.
Right. So really our force is going to come, and it's in this case going to come exclusively from the weight of the cable. Is that weight going to be constant?
No.
No. It's because as I pull this rope, this cable up the side of the building, once I've pulled some of it onto the spool, I'm not carrying its weight anymore. I'm not lifting. So let's do this. Let's define a variable. Let's call this place right here x equals 0. And we'll say x is the length of cable that has been pulled to top of building. So this force right here, we've already decided, is not going to be constant. So we need to figure out a way to write a function for this force in terms of x. So one way I think is a good way to organize that is to do a table here. So let's just come up with a couple of xf pairs. We'll start with an easy one. If x is equal to 0, what's the weight of this cable going to be?
£200.
Going to be 200 pounds. Let's go to extremes and maybe we'll work backwards. Let's say x is equal to 40. What's the weight of the cable in that situation?
Zero.
Should be 0. Yeah, I've pulled it all up. It's not, I'm not carrying any more of it. Do we think that's going to behave linearly? In other words, is this going to be true? Can I assume that if I pull up half the cable, that I'm only dealing with half of its weight?
I feel like it would have to be an unusual cable for it. Like, maybe I'm thinking about it wrong, but like, I feel like that should be true.
Yeah, I mean, we can assume that the cable is uniform. Otherwise, yeah, it would have to be an unusual kind of situation. So I'm going to delete this question mark. So I think this is a good, these are 3 good data points for the weight of this cable. So now from that, can we define, can I write an expression for this f of x? And really what I'm doing here is we're going to write a linear function. So we've kind of already, we've justified that this will have a linear relationship between x and between that displacement and that force.
Oh, would we just define the rate of change?
Yeah, and then really, yeah, you can define the rate of change. So yeah, well, that's one way to look at it. Or we have 3 data points here. You can just find the slope and then find the y-intercept. But since you brought it up, let's talk about that rate of change. Do I know how much each foot of this cable weighs? Can I figure that out?
Just 200 divided by 40.
Yeah, so that, and we'll call that the density. Really, that's the linear density of this cable is 200 pounds divided by 40 feet. Or if we simplify, 5 pounds per foot. And I think from there, we can write this expression because I know that when x is equal to 0, that my force is 200 pounds. So kind of get our y-intercept for free. And I know that for every foot that is raised of the cable, I lose 5 pounds. So are we okay with this this definition here for the force in this situation?
Looks good.
So from there, I can start filling in my integral because I know what the force is. I'm going to leave the limits of integration for now, but I'm integrating 200 minus 5x dx. And if I want to find the work done to lift that entire cable up, what should my limits of integration be?
Zero to 40.
0 to 40. Yep. And since the setup is the most important part of this, I'll go ahead and stop here for now. Anybody have any questions about how we got here? How we set this up? Okay, this is a pretty simple integral, at least to compute. So I'll get started doing that. If you have any questions about how this was done, please ask me. Oh, I missed something terrible.
So pound is like force.
Yeah, pound is a measurement of force. I mean, I think we're all used to thinking of pound as a measurement of weight. And weight is it's a specific type of force. It's the force of gravity. So weight, I mean, I think the first way I described weight or described a force was a push or a pull. Weight is the pulling force of the earth on an object. So yeah, it's absolutely weight's a force, which is why it makes sense for us to talk about weight in terms of newtons or pounds, depending on what system we're dealing with. And I think I get a final value of 4,000 foot-pounds. Any questions about any of this before I move to our next thing?
I had a trouble trying to understand the 5x part. Like,
Yeah. So let's go back to the beginning here. So the whole cable weighs 200 pounds. So when x equals 0, that means the entire cable is hanging down. So at the moment I start lifting it, I have to bear the weight of the entire cable. But as I start to pull cable up, then I basically think about it, I get to pull the cable up and basically start piling it up on the side of the building next to me. And I am no longer holding that part of the cable.
Hmm.
So if I assume that this this cable is uniform, basically it has, this constant density to it, then that means that since I know the cable weighs 200 pounds and is 40 feet long, I can assume that every foot of it weighs 5 pounds.
okay.
So that's why, if x equals 1, let's say I've pulled up 1 foot of the cable, then now I'm only holding 195 pounds. of this cable. So basically that -5 is like, that's my constant rate of change. That's my slope. That's the weight of this cable as a,
But can I add something? So
Yeah.
what if we sort of like consider the 200 pound cable as a 200 pound ball
Okay.
moving through 40 feet long distance? Like, wouldn't that be the same thing, I guess?
Not really. I think the problem here is if you have a 200-pound ball, you know, it's hard to think, it's hard to break down that ball into like these little discrete chunks. So let's say you're pushing that 200-pound ball. Let's say you have to push with 200 pounds of force to move it 40 feet. Then that force is constant because, you know, you have to move the whole ball all at once. So to move that ball 40 feet, I'm constantly having to apply 200 pounds.
Mhm.
I feel like that would be a combination of, like, assuming the ball is like at the end of a cable, then
Yeah,
it would be kind of like a combination of the two
yeah.
problems.
And I have my example coming up next, I think will kind of point out those distinctions, but let's say I did have a heavy cable and on the end of that heavy cable was a ball that had another weight. Then that weight of that ball is going to be constant because I'm always carrying it because it's at the bottom of the rope. But as I pull the rope up, the weight of the rope is decreasing because, you know, when I pull it up and set it aside or put it on a spool or however you think of it, then that weight, like I have lifted that weight. I'm not still lifting it. Hopefully that's a little more clear.
That's clear.
And I think that'll become even more clear when we do our next example here, because this involves, you know, that was one weight we had to deal with. This is going to be multiple. So I have a 10-kilogram bucket, which Rias is like a good analogy for the ball you just mentioned. I have a leaky 10-kilogram bucket. I'm lifting it from the ground to a height of 12 meters. The rope has weight to it. The bucket has water in it, but the water leaks out. So our last one we were dealing with, we had one weight to deal with. How many weights do I have to consider this time?
I feel like it's the same question almost.
There are parts of it that are similar, but it's definitely not going to be as simple
Yeah.
as the last one.
Yeah, so it would be a changing weight with the rope and a changing weight with the bucket.
Not with the bucket itself, but with the water.
Well, the water, yeah, water.
So let's talk about this. We have the water. And we mentioned the water and the bucket. So those are two different weights we have to consider separately. Is there anything else we need to talk about?
The rope.
The rope. So yeah, there are three weights we're going to have to deal with. So basically our force is going to be this, or our force in terms of X is going to be the force with respect to the water of X, plus the force with respect to the bucket of X, plus the force with respect to the rope. So one of these is really easy. So let's just get that one out of the way.
The bucket.
Yeah, the bucket is a constant all the time. So the force of the bucket with respect to X is just 10 kilograms times 9.8 newtons per kilogram. So that's 98 newtons. So that's simple. All right, so I'll leave it up to you all. You want to handle the water or the rope next?
The water.
Okay, let's do the water. All right. Can I use a constant rate of change for the water?
It says that it leaks at a constant
Yep.
rate of,
I am allowed to use a constant rate of change. And you know, I keep using the variable x here. Let's define x in a similar way. So basically the displacement upward from start.
But Professor, I have a doubt.
Sure. So
How do what if how do we know like the constant rate is sort of like a variable, right? Like I mean it is constant, but it's like but it could vary, right? Like depending on how deep the the how much it's leaky or something. Like
yeah, I mean, that would probably have an effect on it, but in this problem, we are told to assume it's constant. But yeah, you're right. If there's more pressure acting on the water, so if there's more water, it's probably not really going to be constant. But in this case, we're going to assume that it is.
oh, no, not that. Like yeah, it is constant, but that but how do we know like which constant it is? Like it could be.
Oh, right. So right now we don't know what that rate is. It's something we have to do a little bit of work to figure out.
Sure.
So that's what I was going to start here is this table. So if we can come up with so we know it's constant, which is good for us because if I can figure out 2 points here, then I can write that equation because I know I'm looking at a straight line. I know I'm looking for a straight line expression for the weight of the water. So what's one data point I know I can lean on to join our displacement x with our weight of the water?
f of 0 equals 36 kg.
Yep. And then remember, we had to convert our masses to forces. So 36 times 9.8. Got 352.8. All right, we got one. And you know what? Because we chose x equals 0, we have our y-intercept, which is convenient. Oh, so what's another data point we can use?
Sorry, go ahead.
Sorry, now I was thinking 12 meters for like X and then I guess 0 for which water is.
Yeah, that's absolutely right. It says that just as I bring it up to the top, the water's going to be gone. So from there, I should be able to figure out what my slope is. So my force of water with respect to x is going to be 352.8 minus whatever constant rate of change you come up with times x. which hopefully you get 29.4.
Oh, so if it wasn't constant rate, it would have been super hard.
Yeah, I mean, in fact, you would need a lot more information from me. Yeah. All right, so we got two pieces of this puzzle. Now we need to figure out the force of the rope. We can probably get by with a table. And I think it's really good practice to make one of our points be x equals 0. So what's the weight of the rope at no displacement?
So we have 12 meters of rope times 0.8 kg per meter.
Yep, so 12 meters times 0.8 kilograms per meter. Is that enough to get to the force?
Would you also multiply it by 9.8?
Yep. 9.8 newtons per meter. Move the chat window, and then I get 94.08. And one thing here, no, this is not newtons per meter, newtons per kilogram. And because this basically, you can get your slope just from this. If I know how much mass is in each meter of the rope, and I know how much force, or I know how much weight goes with it corresponds to a kilogram on planet Earth, that means I can get my slope from here. So 0.8 times 9.8, that comes to be 7.84. So that means I can write my rope equation as 94.08 minus 7.84x. And now that I have all three of those pieces, I know that my total weight that I'm dealing with is just the sum of all three. So my force is going to be, let's just add up all the constants. So I get 98 plus 352.8 plus 94.08, 544.88 minus 544.88, which means my work integral is going to look something like this, leaving the limits off of it for now. 544.88 minus 37.24x dx. And what are the limits of integration that I should use?
0 to 12.
0 to 12. And I'm going to go ahead and just leave it there. I believe in your abilities to compute those integrals, but setting it up is the important part. Any questions about anything here? We did quite a lot. All right. Clear one more thing here. So I have an aquarium. These given dimensions here, and I want to pump water out of it. So basically, let's just draw this. It's a rectangular aquarium. So it's full of water. 2 meters, 1 meter, 1 meter high. Full of water, and I'm going to pump half the water out of the top of the aquarium. So let's just ground ourselves here. I know that my situation is always this here: force as a function of x times dx. So what I'm going to do here, I'm going to, kind of like what we did with our volumes and our, other things we've done with integration. I'm going to take a, like a representative slice of the water in this aquarium, and we're going to think about the situation in terms of that. And basically this slab of water, this slice, has to be basically pumped out of the top. So basically we're going to build this up in pieces. So let's do this first. I want to find the volume of that piece of water. And so before we go any further, let's define a variable. Let's say x is equal to the height from bottom of aquarium in meters. And this little arbitrary slice here, this is going to be dx. It's going to be dx thick. So given that, what is the volume of this little slice going to be? What shape is it?
Cube.
It's it's not a cube, it's a rectangular prism, but its 3 dimensions are going to be different. So really the volume we're looking for is length times width times height. So what are the length, width, and height of this slab of water?
Mm-hmm. 2 meters cubed.
Not 2 meters cubed. 2 meters is the length. I believe it's 1 meter wide. How tall is it?
dx.
That's the dx. So that's where our differential terms going to come in. So our volume is going to be 2 dx. So that's the volume. Now let's build this up into the mass. I know that I'm given that the density of water is 1,000 kilograms per meter cubed. So that means this is going to be, I really should keep units on these because we're going to be dealing with a lot of them. I know that 1 cubic meter of water has a mass of 1,000 kilograms. So this slice of water here is 2,000 dx kilograms. All right, so we started with volume. We translated that to a mass. What's the next logical step in this sequence? What's the next measure I should try to get? Keep in mind that to have a chance at dealing with work, I have to get to a force, right? What's my link between mass and force? What's the weight of a kilogram? How do I find that?
Isn't it 1 cubic meter of water?
Oh yeah, so we've gotten mass, yeah. But now how do we get to a weight from there? From that mass?
Convert it to newtons.
Yep. So gravity on Earth, 9.8 newtons per kilogram. So now I have this force is, what is this equal to? 19,600 dx, and that's now in newtons. And here's the part that makes this one a little unusual. In all these other examples we've done for work, our dx is usually our placeholder for the distance. In this case, this dx is a placeholder for basically where I am, where this water is in that tank. dx is basically a height variable. So because of that, our work is going to be, basically our distance is not going to be dx like you're used to. So let's start building up the integral. I know our force is equal to 19,600 dx. So this is my force. What do I have to multiply force by to get work.
Distance.
Yeah, so I need a distance here. So now let's talk about what that distance is going to be. So remember, to pump this out, I'm going to have to pump the water out at the top of the aquarium. So what water is going to be hard to pump out of the aquarium? Water near the top or water near the bottom?
I feel like maybe I'm overthinking it. Like, I feel like, yeah, water near the bottom would require more work,
Yeah, so
right?
it has to travel further. So, I mean, the force I found here, that force is going to be true regardless of where you are. Basically, no matter if I were to draw this rectangle anywhere, that weight's going to be equal. So the difference in work is going to come from how far do I have to push that water? Let's take it to the other extreme. If I have, let's say I wanted to take this thin layer of water at the very top, I'm really doing no work on it because assuming the spout is at the very top, like I don't really have to make it go. I don't have to displace it. So because of that, and I'll just fill this in and we can talk about why this is the case. My distance here is going to be this expression, 1 minus x. And remember what we said x was going to stand for. The height from the bottom of the aquarium. So really the water at the top of the aquarium requires no work to be pumped out because it's not going to travel any distance. The water half a meter down is going to have to, actually, let's not pick that number. Let's say the water 0.7 meters down. The water 0.7 meters below the surface is going to have to be displaced 0.7 meters. So basically, our work is going to, or our distance is going to, be opposite of the way we set up this variable. Are we okay with that? All right, last thing here, the limits. We want to pump out half the water. By the way we've described this, is that going to be the top half of the tank or the bottom half of the tank? Think about what you would have to do to pump out the bottom half of the water. If you pump out the bottom half of the water in the tank, it's all coming out. So because of that, we're only pumping, we're going to pump the top half of the water out of here. So because of that, what are our limits of integration going to be?
.5 to 1.
0.5 to 1. Yeah, all the stuff that's on the bottom half meter of this tank is going to stay where it is. So this is going to be my integral. So the integral from 0.5 to 1 of 19,600 minus 19,600x dx. And half of 19,600 is 9,800x squared. And I did this in advance, but check me anyway. But I'm pretty sure that's the work, is 2,450 joules. Any questions about anything we've done in work? Right, I'm going to close this presentation. We're going to move on to chapter 7. So Ask-
Actually,
go ahead.
sorry, just a quick question. So when we're offered problems like this, should we always think in terms of what would use like the least amount of energy? Like, because I feel like a pump in real life would always go to like the bottom of the body of water. Like, you know what I mean? Like,
Yeah,
yeah. So should we just, in terms of problems like this, just think of like what would use the least amount of energy?
so I'll tell you the section of the book that I got this from, or the ebook, basically said that for all the questions in this section, you're pumping out of the top. So it's not clearly stated here, but it's clearly stated elsewhere. I just brought that fact in, but I think, yeah, if you're talking practical applications, you're totally right. Yeah, why fight gravity if you can make it work for you?
Okay, great. Thank you.
No problem. Anything else? All right, I'm gonna have to bag this when we can come back to it if we have time. All right, so we're moving on to chapter 7 now, which is basically a kind of a grab bag of integration techniques. So first one we're going to be talking about is integration by parts. Oh no, I take it back. I almost walked away from the whole section in chapter 6. So I was talking about average value of a function. So we want to find basically the average value of a function. So before I tell you what that means, let's just kind of think about it. So I've given you a curve here. Has a well-defined left and right endpoints. What does it mean to find the average value of a function? What do you think?
Average between the 2 points.
So yeah, if I can do, you know, f of 1 plus f of 5, divide that by 2. Okay, anybody else have any ideas? So typically when we average something, you know, we take the number of values there are, add them all up, and divide that by the number of values. So yeah, if we average out these 2 points, we can find the average values of those 2 points. How many points are on this curve here?
Infinite, technically.
It's an infinite number of points, right? So, you know, I could start taking points, adding them up, but if I did it that way, I would never be done. So basically what the average value is basically what I want to do is this. I want to take this curve here, and if I can possibly find some value it would basically, if I can make these areas the same. So if I find the area under this purple curve, I would love to be able to find a constant where I could get the same area over the same interval. So basically that's what average value is going to do. So let's take a look at, well, actually, let's go ahead and do it here. So we want to equate these areas. So tell me first, if I'm not telling you what this function is, I'm just going to call it f of x. How would I find the area associated or define the area under this function over this interval? So we did something a little more complicated than this by finding the area between curves. Now I just want to find the area underneath a single curve. So what operation is needed to find an area? All right, I'm hoping that somebody is thinking integration. So if I wanted to find this area, that would be the area from 1 to 5 of f of x dx.
By integral dx.
What's that?
If we're finding the average value, is it divided by integral of dx?
Dividing this by the integral?
Yeah.
Well, I mean, this is the integral. If I divide it by itself, as I'm
No,
sure.
no, no. If dividing that by the integral of dx, not f of x dx.
Oh, so
Would that
divide this by 5 of 1 by like this?
Oh yeah, would that give the average value?
Let's talk about that. I actually haven't seen it done this way before, but I think it's going to be interesting. What is the integral of dx?
Four.
Yeah, in this case, it'll be 4, right? Because the integral of dx is just going to be x, evaluated from 5 to 1. That's 5 minus 1, so it ends up being 4. So yes, you're absolutely right that, you know, if you do that, then you're going to have basically this is the way to go. But you know, you can kind of shortcut all of this and just say, all right, 5 minus 1, basically, because really all that little integral you gave me, Rias, is going to do is basically just find you the difference between the two limits.
Okay.
Yeah, but yeah, you're absolutely right. So if I find this value here, actually, I should stop putting equal signs. Yeah, let me fill this all in. So the area itself is just going to be that integral. And let's call this thing right here, let's call it C. C is going to be this area here, divided by the integral from 1 to 5 of just dx, which comes out to be, I'll leave that one alone. So I know C is going to be that height. And if I multiply that height by 4, I'm going to get that same area. So I'll go ahead and stop there. I think it's important to understand how this is developed before I kind of just spoil it for you. But this is exactly the way you find the average value of a function. If you have, basically I have an infinite number of data points to add up an average. And the only tool we have to add up an infinite number of things is the integral, which is why we have to use it for a continuous function like this. So let's take what we've kind of built here and generalize it. If I want to find the average value of a function or of f of x, it comes from this. It's the integral from a to b of f of x dx. But then to average, we just divide the whole thing by the length of the interval. Stop me if you have questions. We're going to be using this a lot in the next few examples. Okay, I'll keep on going. So same function, now I'm defining it for you. I want to find the average value of f of x equals 2 over x over that interval 1 to 5. So know that my average value basically, let's just build it up kind of the way we did the first one. I know I need the area. So let's find the area first. How would I find the area under this curve over that span of x values?
Integral from 1 to 5 of 2 over x dx.
Very good. What is the antiderivative of 2 over x?
Log x, log mod x.
Yep. So 2 natural log of x. Evaluated from 1 to 5, and that gives me 2 natural log of 5 minus 2 natural log of 1, which is equal to 2 natural log of 5. So we got that area. So what's the average value then? What do I need to do to find the average value?
Divide it by 5 minus 1.
Yep. So yeah, my average value is equal to that integral, 2 natural log of 5, divided by 5 minus 1, which is equal to, in the end, 1/2 natural log of 5. How do we feel about that first one? All right, let's move on to another one. All right, average value of this function, no graph provided this time. I'll let you all walk me through it. How do I find the average value of this function over the interval that I gave you? Someone tell me what to do.
Find the like area first. Do the integral from -1 to 2.
Okay.
Of 1 plus x squared dx.
Good. All right, thank you. So we can definitely compute derivative or integrals. So this comes to be x plus 1/3 x cubed from -1 to 2. I believe that's 6. I'll wait for someone to confirm or deny.
I got that too.
Cool. All right, so from there, how would I get the average value? I'll use a new piece of notation here that you might see.
Do 6 divided by 2 minus -1.
Yep.
Just-
Yeah, so Shaw, his average value should be in this case just 2. That's about it for that one. Anybody have any questions? All right, let's keep on going. So let's talk about the mean value theorem. You have probably seen the mean value theorem when you talk about derivatives. Here's its counterpart when it's we're talking about integration. So if you have a continuous function f on some closed interval AB, there must exist some c inside that interval such that the average value is equal to f of c. So basically, as long as that top condition is met, as long as your function is continuous over some interval, there has to be some value on the interval where this is true. So just in English at the top and in mathematical notation below, basically, whatever my average value is, there's got to be a c that if I plug that c value into my function, I'll get the average value. And since that is guaranteed to exist, we should be able to find it if I give you a situation. Or another way to represent it as well. Really, the only difference from one to the next is that I just multiplied both sides by b minus a. All right. So in the last example, we had the average value was 2. And just to remind you, our function was 1 plus x squared. So what value of C satisfies the mean value theorem? So our average value was 2. So there's got to be some f of C out there that equals 2. So how would I find that value of C? Can I say f of C some other way? So remember, I know what f of x is equal to. So because that f of C, I can just substitute C in for my variable and I get 1 plus C squared equals 2. So really from here, it's just a matter of solving my equation. So then I get C squared equals 1. And because of that, I get C equals -1, +1. And since both of those are inside my interval, then the mean value theorem guarantees that I have one value of C that fits, but I may have more. In this case, I have 2. Actually, was it 1 minus x squared on the previous example? No? Okay, good. All right, any questions here? All right, let's keep on going. And I think this is my last one. Yeah, it is. Okay. All right, so I want to find the average value of this function on the interval 0, 8. So no, can't integrate it in a traditional sense this time, but we can still find the average value. So what would I need to do to find the average value? Give me a good first step.
Find the area under all the, like the graph.
Yep, so got to find the area. Might be best to do that in pieces. So let's do this. One shortcut I'll kind of lead you through is this. What's the area from 0 to 2 of this function?
0.
Should be 0, right? I have basically this area and this area are going to be identical. Well, they're going to be opposite because one's below the x-axis, one's above. So that means they're going to cancel each other out. So next logical step here is to find the integral from 2 to 3. What is that?
Can we sort of like simplify it way more, like that from 6 to 7 you could just bring it to 2 to 3, and 7 to 8 you could bring it to 3 to 4. It's like because it's symmetric. Flip it. I don't know.
I don't think I see a lot of symmetry going on here.
Oh, that 6 to 7. Um, wait, you can add 2 to 3 to like 6 to 7.
Add 2
Um,
to 3. Let's see.
okay, I'm not saying 2 to 3, like that from 2 to 3, that area under that, you could just bring it to 6 to 7. So that would make a rectangle.
Oh, I understand. Okay, so then I'll say this. I see what you're saying. If I add those two things together, that's a good idea. So bring this little triangle and basically superimpose it here. So then what would that area be?
2 times 3, 6.
Yep. That's a 2 by 3 rectangle. So that's 6. All right, so now we need from 4 to 6 and 7 to 8. Oh, wait.
You can
Nope,
again
nope.
impose it.
No,
like
you're
that.
right. We did 4 to 7, didn't we?
Yeah, and 7 to 8 also you could sort of like do it because 3
Oh,
or
okay.
4 could be like,
That's really, really clever. Very cool. So yeah, if we add 3 and 4, or the integral from 3 to 4 to the integral from 7 to 8, then you can generate another rectangle
that's
that
3.
has an area of
3.
3. So all told, I get the integral from 0 to 8 of f of x dx is equal to 9. Not sure I ever would have thought to look at it that way, but it's really clever. Any question about how we find the area, or basically the integral over this value, over this interval? All right, so got the area. Then how do I get the average value?
Divided by 8.
Yep, so our average values can be 9 divided by 8 minus 0, or 9/8. All right, so let's underline the things that are important. Value of the integral, average value of the function. So let me ask this. This function is continuous, so I must have some value that makes this happen, because the mean value theorem guarantees it. How many values am I going to have? So how many c values am I going to have? Obviously, it's going to be 1, because the mean value theorem guarantees 1. But do I have more? So let's look at it. 9/8 was approximately here, a little more than 1. So hopefully you're seeing that basically I can identify 3 of these things: C1, C2, C3. And we could use some algebra to find these exactly. I don't think that's the best use of our time. So we'll approximate. And let's say I want this to be true. So what's that first value? That's C1. Someone give me an approximation for what that's going to be.
3.7.
3.7, you said?
Yeah.
That sounds reasonable. And how about the next one?
Like 6.9.
6.9 sounds good. Which would sort of dictate that the last one had to be, I'm just gonna say 7.1. I know that it's more than 7 for sure. Any questions there? So average value of a function, mean value theorem are the two big takeaways from that section, but it's a pretty quick one. Any questions before I send us to a short break? Okay, I have 7:42. Why don't we all come back at 7:52? And I'll see you then. All right, I have 7:53, so let's go ahead and get back to it. Before I get back to calculus, one thing I want to remind you is if you haven't been checking the syllabus, our first test is on the 1st of June, which is a week from tonight. So just a reminder how that's going to go. I will be doing basically the last half of class on Thursday is going to be, a kind of a quick review of everything that's going to be on, basically all the sections that are going to be on that test. Over the weekend, I'll post some things on Canvas that you can use to get some more practice on. And then on Tuesday, the first half of Tuesday will basically be, optional attendance. From 6:10 to 7:40, you can basically, I'll be here. You can ask me whatever questions you want about, old homework, old quizzes, some of the review things I'm going to put on Canvas later this week. But basically that time is yours. I really recommend everyone show up and have some questions that, that they can get answered to kind of close some gaps before the test happens. But at 8:40, that's going to happen. So reminder that office hours are Tuesday, Wednesday, Thursday at 5:30, just in the same place. So if you need anything, come sign on to class early and I'll get you whatever help you need. But yeah, this first test, June 1st, is approaching quickly. So if you need anything, please let me know. All right, so chapter 7, basically, we're not going to go through every section in chapter 7. We're going to go through most of them, but basically these are all, a bunch of different integration techniques that you haven't seen yet. So first one's called integration by parts, and to kind of motivate, where it comes from, let's do this. So actually going to find a derivative. So I'm giving you the function x e to the negative x. How do we find that derivative? So what tool do we need to find a derivative of functions like this?
Wouldn't the antiderivative of x e to the negative x, wouldn't that be negative x e to the negative x?
Not quite.
Might be.
But yeah, we're not doing antiderivative yet. We're doing just a derivative first. But for functions that look like this, what rule do I need to use?
I think it's I know e to the x is e to the ax equals I think a e to the x. It might be forgetting the rule.
No, that's about it. Basically, this is a specific application of the chain rule. But really, I can't really combine these two. Basically, this function is two more basic functions multiplied together. So what differentiation rule am I going to have to take advantage of?
The product rule.
Yeah, I need a product rule. So how does that work for this derivative here? Or for this function?
So if you have f times g of x, I believe it states that it's f prime times G plus G prime times F.
So I'll write it like this. So the derivative of, and because I've already used the function handle f, just do it like this. But yeah, basically derivative of one times the other plus the derivative of the other times the first one. So that's basically what we have going on here. So in this case, the derivative of f of x is going to be g prime of x will be 1. H of x is just e to the negative x. G of x is x. And h prime, we're just going to take advantage of this rule here. It'll be negative e to the negative x. And putting that all together, you get e to the negative x minus x e to the negative x. So a little bit of hopefully review. I'm sure you did some product rule and calculus, probably a lot of it. Basically, integration by parts is, you know, kind of the antithesis of that rule. And that's why I think this name is a little, this name hides that fact, but really integration by parts is the product rule for integration. So basically, let's look at it this way. If I am taking the derivative of this kind of thing, f of x, g of x, then I get, you know, f prime of x, g of x, plus f of x, g prime of x. So now what were to happen? So let's kind of go the opposite direction. Let's say I already have the derivative and I want to anti-differentiate it, take the antiderivative, find an integral. So that means basically, first let's just copy everything down. But I want to integrate this thing. Basically, if I were, let's say, you know, the derivative we just found, let's say I wanted to integrate that and get back to where I came from. Then basically I have to integrate both sides of this equation. So let's talk about what this is going to look like. So I'm integrating a derivative. Those are inverse operations of each other. So this is just going to give me f of x, g of x. And then these other two things are going to be f prime of x, g of x, and plus the integral of f of x, g prime of x. So basically what we're going to be doing is this. We're going to be using integration by parts to, and really, hopefully you can see these things are absolutely symmetrical. I mean, it's really, f and g are generic functions. I could easily just trade their names. So really these two things are identical. So basically here's what integration by parts looks like. If I want to find the integral of some function like this, so f prime of x, g of x, that is going to be equal to f of x, g of x minus the integral of f of x, g prime of x. And I'll give you another way to look at this. Kind of the more traditional, more compact way you'll see this is like this. The integral of v du is equal to uv minus the integral of u dv, where u and v are functions of usually x, whatever your independent variable is. So I'm guessing that'll be new to most of you. Okay, so this is what integration by parts looks like. It's basically a reapplication of the product rule of differentiation, basically going the opposite direction. Any questions so far before we start using it? Okay, let's do it. So I'll kind of walk you through this first one here. So we have this integral x sine of x. You know, at present, you don't really have a good tool that's going to help you integrate this. So that's what integration by parts is for. So I'm usually going to use the more compact version of this. So v du equals uv minus the integral of v du. So basically the way we need to start this is we have to identify, you know, basically I have two smaller, more simple functions that I'm multiplying together to make this function x sine of x. So I want to call one of those things v, and I want to call one of them du. Hold on. Sorry. Use the same thing twice. This really should be the integral of u dv. So I like to make this a little quick 2x2 table. And just a kind of rule of thumb here, when I say you're going to call one of these pieces u and the other piece dv, really what that means is you're choosing that you're going to differentiate one and that you're going to integrate the other. So usually, I don't want to promise you always, but usually the thing to look for is differentiate the one that is going to become simpler when you differentiate it. So let's phrase the question that way for this first one here. Which one of these is going to become simpler when I take a derivative? X or sine of x?
X.
Yeah, it should be x, right? Specifically, what is the derivative of x?
One.
1. So yeah, u equals x, and then du equals dx, which is another way to say that du dx equals 1. All right, so we have decided that u is equal to x, which means we have also decided that dv is equal to sine of x dx. So if we integrate that, what does v become? What is the integral of sine of x, or the antiderivative of sine of x?
Is it negative cosine x?
Yeah, negative cosine x. So once you've done that, you basically have the ingredients. Now it's just a matter of basically, you know, filling in this form here and continuing. So the integral of x sine x dx is equal to uv, which is negative x cosine x minus the integral of v du, which is negative cosine x dx. And since we can, we'll do one little bit of simplifying. And what is the antiderivative of cosine x?
Sine x?
Sine x. So then from there we can take this sine x minus x cosine x plus C. Any questions about this first one? All right, let's move on to something else. So we said a while ago, and actually not too long ago, that finding the integral of natural log of x was something that was not something we could not do. But now, given this new tool, integration by parts, we now have a way to get this integral. Because I get to choose to break this up into two parts, one of which I integrate, one of which I integrate, and the other of which I differentiate. So the tricky thing to look at here is that, this thing isn't really, it's not obvious that I can break this up into two pieces because, I can't split the natural log from the x, for example. They're linked to each other. But let's start with this. I know that, I can't really differentiate, or I can't really integrate natural log of x. So I can't say dv equals natural log of x dx. But what I can do is say u equals natural log of x. The derivative of natural log of x is something I know, something I already know. So I can definitely do that. But my question before we go on is this. If u equals natural log of x, then what's my other part? What is dv equal to?
The dx.
Yeah, it's just dx. That's all that's left. Another way to look at it is that dv is just equal to 1. And this really is what makes integration by parts so powerful, is that basically we're trading an integral that we can't do directly. We're trading that integral for another one that hopefully is easier. So if we can't do it directly, then we're coming up with an alternate approach. All right, so I got u equals natural log of x. If that's true, then what is du equal to?
One over x.
1 over x, yep. Dx over x. And if dv is equal to dx, what is v equal to?
X.
Right, so now we're ready to keep going. So integral of natural log x dx is equal to uv, which is x natural log of x, minus the integral of v du, which is just going to simplify to become 1 dx. So then we get x natural log of x minus x plus c. So this is one thing to keep in mind with the integration by parts. You have a lot of choice over what those two parts is and what those two parts are. So, and that's, where it gives you flexibility, it also poses some difficulty because very good chance you could make a choice that won't get you any closer to being able to do the integral. But I'll give you some advice as we go. We got a few more examples. I'll give you some advice as we go as to how to make those choices. Any questions here for this example? All right, moving on. All right, we got x squared e to the x. So basically our first choice is always this. What is u? And what is dv? And just let's remind ourselves, what's usually a good choice to choose for u? What kind of function anyway?
I want to make it simpler. So
One that'll
x
make
squared.
it simpler. Yeah, in this case, that's going to be x squared. So yeah, in general, polynomials, yeah, when you differentiate them, you decrease their power by 1. So that will usually make them simple. So if we're putting u as x squared, that means dv is e to the x dx. So what is du equal to, and what is v equal to?
du is 2x.
Du is, yeah, 2x dx actually, but yeah, still good. And then v?
E to the x.
Yep. Nice thing about e to the x, it is its own integral and derivative. All right, so now when we start putting this together, we get uv x squared e to the x minus the integral of v to u, 2x e to the x dx. All right, so what do we think? Where should we go from here? Did we make the right choice, do you think? So we're in a place where, we're not going to be able to finish this because this integral right here is, not something we can do directly. So let's pull it off to the side. How do we handle this integral here? What do we have to do?
Would we also have to do integration by parts?
Yeah, we're going to do that again. So just keep this separate. So now I'm going to use u and v again. So there's no doubt. What should I use for u this time?
Two x.
2x. So and this is one of those cases, sometimes you'll have to do integration by parts multiple times. So we can see that even though we didn't get to a place where we could integrate directly, we did, we made progress because we decreased the power on x. We made it simpler. But sometimes it's iterative. Sometimes I have to run through this again. So then this integral is going to be uv, so 2x e to the x, minus the integral of v to u, which is 2e to the x dx. Can we integrate 2e to the x dx directly? Hopefully you're seeing that this will just become 2e to the x. So then I can take this and now go back to my original integral and drop that in for this one here. I'll pause here. Anybody have any questions? Okay, we'll go ahead and keep going. All right. E to the x sine of x. So for this one, got to start with the usual first choice. So I'll leave it to you. What is the, what should we use for u? Will one of these things become simpler through differentiation?
I mean, the fine becomes simpler, like sine x will, can change to negative cosine x, but that's not really simpler.
Yeah. So I mean, and that's a good point. Like, what do I mean by simpler? You know, for example, if I have, you know, x to the 7th, if I keep taking derivatives of x to the 7th, it'll eventually become 0, right? I don't think I can say the same about e to the x. Certainly, if I just keep differentiating e to the x, it'll always be e to the x. If I differentiate sine of x, you know, if I do it once, it'll become cosine. If I do it again, it'll become negative sine. If I do it again, it'll become negative cosine. If I do it a 4th time, it will become sine again. So really, I can't make either one of those simpler. I'm never gonna, you know, I'm never really gonna be able to get rid of one of those. So in that case, let's just pick a path here. I'm going to say u is equal to e to the x and dv is equal to sine of x dx. So we've seen this, the derivative of e to the x is just e to the x, so that'll be like that. And the antiderivative of sine will be negative cosine x. So from there, let's take our first pass at this and see where we end up. So we get uv, so negative e to the x cosine of x, minus the integral of v du. So I'll just deal with that now. E to the x cosine of x dx. So we're in a very similar place now. So now we have this integral e to the x cosine x. So let's give ourselves a new space to work. And we'll take a similar path. E to the u is equal to e to the x. dv is equal to cosine x dx. V is equal to sine of x. and du is equal to e to the x dx. If I follow that, then I get my integral of e to the x cosine x is equal to uv, which is e to the x sine x, minus the integral of v du, which is e to the x sine x, minus the integral of e to the x sine of x dx. So kind of seems like I'm going in circles here. But let's put it all together and see if we can make something out of it. So I know that my integral of e to the x sine of x dx is equal to, let's just bring down what we had before, negative e to the x cosine of x, and then we'll fill this in, plus e to the x sine of x minus the integral of e to the x sine of x dx. I'll go ahead and pause here. I kind of went quickly through that. So first of all, any questions about where we've ended up? All right, if there are no questions about where we ended up, does anybody have any thoughts about how we can continue? Remember, our goal is to get an expression for the integral of e to the x sine of x. So can we use what we currently have to keep making progress on that goal? Do we see this right here, this underlined, basically our integral we want? Do we see this anywhere in here, anywhere in the step we're currently on?
Yeah, it's in that last part minus the integral e to the x sine x.
Yeah, so what ended up happening here is, kind of us going, metaphorically going in circles actually helped us because, I had this integral on both sides of the equal sign. So now I can do this. If I combine them, I get 2 times the integral of e to the x sine of x dx is equal to, and I'll flip these, e to the x sine of x minus e to the x cosine of x. And then I can solve for the integral. So this is a technique that you'll see from time to time where it usually shows up when you have this situation where you can't really pick a component of your integrand and differentiate it to make it more simple. You'll sometimes hear this referred to as a wraparound. So one thing I suggest when you're doing when you're reviewing for the test coming up is, if you want to find some examples, integration by parts wraparound. That's a pretty well-traveled term. You'll be able to find a lot of examples of that. Any questions on this process or how it works or anything? I'm not getting a lot of questions today. I'm hoping that's a good sign. I'm hoping this is all getting through. But yeah, just to remind you, if you have any questions, I have the chat box open, and if you're more comfortable sending me a private message, I can answer that way. But if we're all doing well, that's great too. Let's move on to our next one. Oh, go ahead, Colin.
Question.
Yeah.
So if both parts don't get simpler, do you like know that you're always gonna have to do that wraparound?
That's a pretty good indication. The other alternative is that I just gave you something that can't be done, which is not something I'll do. But yeah, that's a pretty good giveaway. And the key there is, what you've noticed, that I'll introduce another term here of a cyclic or cyclic derivative. So that's really obvious with e to the x. The first derivative of e to the x is the same as the second derivative. It's the same as the 10th derivative. I mean, they're all equal to e to the x. The first derivative of sine of x is equal to cosine of x. But so is the 5th derivative and the 9th derivative and so on. And really, but even like every other derivative, they're just off by a factor of -1. So they're even more similar than that. But when you see that cyclic derivative behavior, that's an even bigger clue that you're headed for this wraparound solution. All right, number 5 here. All right, so we got a definite integral now of inverse tangent or arctangent of x. So I'll take some guidance from you all. What's our beginning decomposition going to be here into u and dv?
Would u be the arctan of x?
Yeah, I mean, so this is kind of like the natural log case where there's only one obvious term that I'm giving. And I'll kind of put it to you another way. Do we know what the integral of arctangent x is? I don't think you do. I don't know what it is off the top of my head, but so that's why integration by parts is so powerful. If you're being asked to integrate something that you don't know the integral of, then you might be able to get to the integral by finding its derivative instead. So when I say that u is equal to arctangent of x, that's really what I'm trying to do. I'm going to try to get this integral by instead letting its derivative work for me. So what's left is that dv is equal to dx, which means v is equal to x. Do I remember the derivative of arctangent of x? These inverse trig ones are
1 by 1 plus x squared. I don't know.
Yeah, that one's 1 over 1 plus x squared. The problem I have with those, I feel like I just feel like arctangent, arcsine, and arccosine are all similar enough they're easy to confuse. But yeah, these are our building blocks here. So let's ignore the limits of integration for now. Let's just try to find the indefinite integral first. So I had x arctangent x minus the integral of x over 1 plus x squared dx. All right, is the integral of x over 1 plus x squared something we can do? Any other integration techniques we've done recently that might be able to help here?
The U substitution.
Yeah, let's do substitution. I'm gonna call it P because we've already used U. But what should we use? If so, now let's try substitution. What's a good expression to try for our substitution?
X equals tan theta. I don't know.
Yeah, I mean, I think you're trying to do a trig substitution. That might work, but there's an easier way to go after this.
Yeah.
Let's do P equals 1 plus x squared. If that's the case, then what's dP equal to?
Um, 2x.
Yeah, 2x dx. And then from there, I'll divide both sides by 2. And that gives me x dx, which is what I want. So x times arctangent of x minus, leave this outside, minus 1/2 dP over P. So what's the integral of dP over P going to be?
Natural log of P.
Yep, 1/2 natural log of P. And then I'll reverse the substitution. So arc x times the arctangent of x minus 1/2 natural log of 1 plus x squared. All right, so that is the indefinite integral. Not quite done because we have limits this time. But any questions on how we got to this antiderivative? Okay. So now the last bit is to evaluate this antiderivative at our limits. So we got 1 times the arctangent of 1 minus 1/2 times the natural log of 2 minus 0 times arctangent 0 minus 1/2 natural log of 1. So hopefully you see that these guys go to 0. What is the arctangent of 1? Another way to think about that is what angle has a tangent of 1?
Pi over 4.
It's pi over 4. Probably easier to think about that in terms of degrees as a kind of a stepping stone. Yeah, your 45-degree angle. A little trig brush up if you need it. Remember that tangent theta is equal to sine over cosine. Sine over cosine equals 1 is just like saying sine theta equals cosine theta. And that's, remember, sine and cosine are only the same if that reference angle is that 45-degree angle. So yeah, we have pi over 4 minus 1/2 natural log of 2. Those two terms went to 0, so this is what we're left with. How are we doing? Any questions on example 5? Okay, let's keep going. Or we'll not keep going. I think that was the last one. All right, so that is all I have for you tonight. We're get done a little bit early. I will stay on till 9:10 if anybody has any questions. Otherwise, the quiz is up now, or at least it should be. I think I scheduled it for to open up at 8:30, so it should be open. I'll stick around for the next half an hour if anybody needs anything. Otherwise, you're free to go, and I will see you tomorrow evening. Remember, the quiz is due at 5 o'clock tomorrow afternoon.
All right, thank you, Professor.
Thank you.